The final talk in this session is going to be on task sequences for remote laser welding in the automotive industry. And this talk is going to be given by Andras Kovacs.
Okay, thank you very much. So I would like to talk about integrated task sequencing and path planning for remote laser welding. And let me start the talk with a short video on the technology itself. So remote laser welding is a recent joining technology that consists in welding metal sheets by a laser beam while the welding robot just moves around the workpiece in a large distance. This is about 1 meter. And the automotive industry likes this technology mostly because it does not require a contact between the robot and the workpiece. So it just eliminates the usual accessibility issues that other welding technologies like resistance spot welding have. And this is good for 2 reasons. First of all, it is fast. It is said that a laser welding robot can replace up to 5 spot welding robots. And also it is cheap. And also for the very same reason, it eliminates many earlier design constraints on the product design. And the industry can easily turn this into car bodies with reduced weight, but yet higher stiffness. On the other hand, this is new technology, and it needs new techniques for process planning. And our general objective was the development of an offline programming toolbox for RLW. And in this talk, I would like to speak about task sequencing and path planning. Okay, so a typical laser welding robot has 4 mechanical joints. And at the end of the robot arm, there is a laser scanner that contains 3 additional optical joints. These include 2 mirrors and 1 focus lens for positioning the laser beam. And it is important that the optical joints are very quick, so the laser beam can jump from one position in the 3D space to the other. Also, the robot can move continuously while the scanner is welding. So in the ideal case, the welding operation looks like the robot moves continuously while the laser beam just jumps from one welding stitch to the other. Okay, so task sequencing and path planning problem then consists in sequencing those welding stitches and finding a scanner path for processing this sequence. We make some important assumptions. First of all, we assume there is a single welding robot, and we would like to perform path planning in the 3D space, mostly because it is much more efficient to perform all the needed geometrical calculations in the 3D space than in the robot joint configuration space. As I was saying, collision with this technology is not a really serious issue, so we postpone collision avoidance after path planning. And we make a last assumption. Actually, there was some debate on this among experts, but the final conclusion was that any task sequence can be feasible. Okay, so then our output consists of the part design. It also includes the set of welding stitches that must be processed. So these are our welding tasks. And a couple of robot and technological parameters. Most importantly, these parameters include a maximum inclination angle, so that is the maximum difference between the laser beam and the surface normal, and also the minimum and maximum focus length. So these 2 together, the inclination angle and the focus range, define a truncated cone for each welding stitch. And then the robot path is a trajectory in the 3D space that spends sufficient time in each such truncated cone to process the corresponding welds. Our objective is minimizing the cycle time, and we also have a secondary objective of minimizing the path length. So basically, just to eliminate unnecessary zigzags or minimize jerks. Okay, we'll take a hierarchical approach where the master problem is task sequencing, and the slave problem is path planning. So the task sequencing problem can be regarded as a generalized TSP problem. It is TSP because we are looking for an optimal sequence of the stitches, of the tasks. And this is generalized because here we don't have the distances in closed form, but we'll have to solve a path planning problem for each of the candidate sequences to evaluate the sequence. Still, we have solved this problem using adaptations of classical local research techniques for TSP and some customized algorithms for a specific problem. So, namely, we generate an initial solution using the farthest insertion heuristic, and then improve this solution using a taboo search with the two opt and or opt neighborhoods. We have developed some custom lower bounds for filtering the neighborhoods that give lower bound on the path length. And actually, we were able to eliminate more than 90% of the candidate neighbors from these neighborhoods. For the remaining about 10%, we'll have to perform path planning. And we are doing it in the continuous space. With our assumptions, we can know that the optimal solution is a broken line that has one entry and one exit point for each of the truncated cones. So this way, this is a rather simple path planning problem. It is a convex optimization problem. So we can hope that if we make an iteration of local adjustments, then it will converge to a global optimum. And this is exactly what we will do. In each iteration, so that is for each candidate task sequence, we will depart from the path belonging to the previous iteration. This is a feasible path. Actually, not quite good at the points where our neighborhood function made some changes to the task sequence, but we'll depart from this. And we'll make a series of local adjustments. So each adjustment refers to one of the entry or exit points, and we will look for the locally optimal position of that specific point, given that its neighbors are fixed. Okay, so we can find that locally optimal position by simple geometrical reasoning in closed form. And so basically, these algorithms will give a rather good good path that is efficient regarding the cycle time. So the next step would be evaluating this path from the collision aspect. Actually, this has been developed, this is ongoing work, and it has been done after the submission of the paper. So anyway, the core idea is to do it only for the final path, check the path, and if there is any collision involved, then relax only the affected area in the path, keep the task sequence, and adjust the path based on the collision map. Okay, so here we have a sample problem. We've carried out experiments on car door designs coming from the industry. So such a door typically contains 50 to 60 welding stitches. And for this specific car door design, the estimate of our industrial partner was that they would be able to do it in 35 seconds. Actually, running our algorithms, it turned out that it is possible to weld it in less than 25 seconds. So I would say that our partner's estimation was really poor. Actually, the estimation was not based on a specific path, but it was based on some rules of thumb that they used typically for submitting their bids to the car manufacturer. But anyway, I think that this result emphasizes that industry needs support in performing process planning in this area. Also, it should be remarked that we have found a single collision on the computed path. It was a collision between the laser beam and the workpiece. and it could be fixed simply by slightly adjusting the path, and it resulted only as an epsilon increase of the cycle time. Actually, for these doors, the problematic stitches are the inner welds on the halo, the window frame, because then when welding one stitch, the robot scanner can hit the other side of the door. Okay, we performed computational experiments on different kinds of car door designs, and we could compare our algorithms to the only approach that we have found in the literature. The reference is displayed here. And that approach is based on decomposition. They first compute the task sequence based on solving a TSP over the stitch positions, and then compute a robot path. So actually, this was not really a good idea from them, I think, because neighboring stitches can have completely different surface normals. So when moving from one stitch to a nearby stitch, it might happen that the robot scanner must move completely to the other side of the door. And this is illustrated on the figure at the bottom. So you can see the red line, which shows that the robot scanner will move in a zigzag around the door. As opposed to that, our approach will find a much smoother and much shorter path. And for this reason, it turned out that in some cases, we can be like 4 times faster in cycle time compared to the previous approach. Again, this is because the car doors had a much more complex geometry than their typical problem instances. Also, it is very easy to improve on that decomposition approach by simply taking the bit points of the truncated cones instead of the stitch locations. And in that case, our solutions were 5 to 10% better in cycle time and up to 40% better in idle time compared to the decomposition approach. And I would say that this can be considered as the benefit of integration versus decomposition. Okay, so to conclude the talk, we have presented an integrated task sequencing and path planning approach specifically for remote laser welding. And we have shown that integration is feasible and it outperforms decomposition approaches. Of course, this is a work in process. The first steps in future work would be the refinement of collision avoidance, the integration of the approach or the algorithms into the offline programming framework, which also must include the definition of possible user interactions to enable mixed initiative usage. And in the long run, we would also be interested in extension to workpieces with more complex geometry, like, for example, complete body in white, and also considering multiple welding robots. And I think that this extension would require handling the collision aspect more in a more refined way. Okay, thank you for your attention.